In his presidential address, Benjamin Pierce cautioned that mathematics should not become a toy or an idol, but should be used for the benefit of mankind and the glory of his creator. First thing about matrices is how I identify them. We identify them by rows and columns. So if I were going to do the dimensions of a matrix, I would say I would list the matrix itself, which is listed usually with a capital letter. Sometimes they list them different ways, but most of the time it's a capital letter. Sometimes they'll name it if it stands for something, so if it's in a word problem, they'll actually name it. But most of the time it's going to be a capital letter. Your dimensions are row by columns. You're going to want to list your rows first, which in this case would be 3, and then your columns second. So this would be a 3 by 2 matrix. When we say rows, those are the ones going horizontally. That's what you count. Columns, think about columns on like a building. Those go this way. So this is 3 rows, or this is, if this were 3 rows and 2 columns. So if it were like right here, then we would say that would be a 3 by 2 matrix, okay? Lowercase represents a specific element within a matrix. So if I am in matrix A, then my elements would all be listed as an A. And then the 2 little numbers right here tell you which row and column to go to. So if I say, well, I'm going to go to row 3, column 2, that doesn't mean A sub 32. That means row 3, column 2. That's this guy right here. Okay, so that's what the little numbers represent. They tell you how to get there. It's like a map, all right? Those are dimensions. So if we look at this, and they give us some special cases, so we'll talk about this. 2 rows by 3 columns. This would be a 2 by 3. This is 1 row by 2 columns. All right, so this is a special case. This guy would be 1 row by 2 columns. All right, this one would be 3 rows by 1 column, also a special case. And this would be 3 rows by 3 columns. If they wanted me to identify row 2, column 1, that would be 3. Row 1, column 2, that would be 2. Row 2, column 1, that would be -1. Row 3, column 2, that would be y. So you can easily go through and find which element they're talking about. Special case, this is called a row matrix. That makes sense because the whole matrix is just 1 row. Then this would be a column matrix, right? This is actually a square matrix when your dimensions are the same, which also makes sense because squares have the same dimensions, right? So that's just some of the details that they're telling you in here. Equal matrices, they have the same dimensions and the elements are the same. Corresponding elements means elements that line up with each other. So in order to have corresponding elements, you have to have the same dimensions, all right? Which is one of the rules that takes us into operations. So if you look at the very bottom of that page, they talk about matrix addition. Matrix addition. With matrix addition, you must have the same exact dimensions or you cannot add them. So if they gave you 2 matrices and said add them and they were different dimensions, you would say undefined, and I cannot do that, okay? So if I look at this guy, they want me to add these up. A and B, that is 2 rows by 3 columns, 2 rows by 3 columns. I can add A and B. And to add them, it is as simple as it sounds. I'm going to add corresponding 3 plus -11, -2 plus 0, 1 plus -4. Just watch your positives and negatives. -4 plus 5, 5 plus 9, and 7 plus -3. That would be my answer. Just add your corresponding parts, all right? If they told me to add B plus C, I have an issue because B is 2 rows by 3 columns. C is 2 rows by 2 columns. So I can't add those. I would actually say that's not possible to do. And so I would say undefined there or, empty set. I can't do that. All right? Cannot do that because you're going to not have a corresponding part to something if you do it that way, okay? So just like in any other world of math, scalar means we're going to multiply everything by the same thing. That's what scalar means, all right? Means that when we're, enlarging things in geometry, it also means when we're dealing with matrices. A scalar is a product. but it's not multiplying matrices. It is just multiplying one matrix by one number. All right, so you can think of it as distribution. They do mention a zero matrix. So we do have a zero matrix. When you have a zero matrix and you're adding it, you're going to keep the same thing because you're adding zero to everything. It is called the identity matrix for additive. So additive identity matrix, just like zero is the additive identity. And for every matrix, you have an inverse matrix, an additive inverse. We'll talk about inverse matrix multiplication. But additive and inverse matrix just means they're all the opposite, so that when you add them together, you get a zero matrix. That's exactly what it means with numbers. If I have 3, the additive inverse of 3 is -3. Because when I add them together, I get 0. So that's all it means with matrices as well. It just applies to every single element within the matrix. You have to do the inverse of every single element to come up with that inverse. So they do tell you that subtraction is just adding the inverse. You can also think of it as subtraction. You just have to subtract each element. Number one problem here, if they want me to do something like this, you think of it as order of operations, 2b minus a. Distribute your 2, subtract those 2. So if I were to do this one, I would say 2 times b, and then minus my a, right? And so I'm going to literally just distribute this guy to all of those first, and then I am going to subtract. So I'm going to say 4, -26, -16. That is that minus this guy right here. And so when I am subtracting these, then I need to keep in mind that I have a negative here. So like it's 22 minus a -9, right? And so that's where we have, I mean, honestly, the difficulty is just to make sure that you remember what you're doing. 4 minus 4, that's easy. Again, -26 minus 24. So we're going to say a -50 here. And then -16 minus 16, -32. So pay attention to your positives and negatives. That's really the most difficult part of that. These, notice, are matrix addition, which includes subtraction if you change it to adding the opposite, and scalar multiplication, not matrix multiplication. Those have a different set of properties, okay? So this is just adding them and distributing them. Commutative property. It doesn't matter what order you add them in. If it's all addition, you can put parentheses, it doesn't matter. The scalar, just like distribution, it doesn't matter which side it's on, that doesn't matter. Associative property, so if I'm multiplying by two scalars, it doesn't matter how I do it. I can multiply the two first, then distribute. I can distribute, then multiply. Distributive properties, if you have two matrices and one scalar, you can put it into both, or you can add them and then distribute. If you have two scalars, you can put them on each one. It's almost like factoring out is all they're saying. It works for these as well. There is an additive identity. If you add the zero matrix to any matrix, you get the one you started with. Additive inverse, if you add two of those, you're going to get zero. And then there is an identity property. So the identity matrix is multiplied and you get the matrix you started with. And if you do not remember what the identity matrix looks like, remember it's just ones in the diagonals and then zeros everywhere else. Identity. So no matter what your square is, your identity is going to be that diagonal of ones and everything else zeros. All right. This is matrix multiplication. It's different than scalar. Scalar means one distributed through. Matrix multiplication means two matrices and I'm multiplying them. All right. Two things you have to know first is, does it work? And if it works, what's my answer going to be? All right. So the first thing I always tell you to look at are these inner dimensions. Row by column, row by column. The inner dimensions have to match. If they do not, you cannot multiply them. So order matters. If they tell you to multiply A times B, you must do it in that order. It's not the same as multiplying 2 times 3. It doesn't matter what order you multiply those guys in. But matrices, it matters. So the first thing we're going to look at are those inner. Do those match? Yes, they match. Then I can multiply. The next thing we're going to look at are the outer terms. That tells you the dimensions of your answer. This is a good quick check. Did I do it right? Because if you look at this, you know immediately what your answer is going to be, the dimensions of it. And then if you do it wrong, your answer may come out wrong. So then you can double check it. They tell you this, all these words, right? For matrix product. AB of the M by N matrix M and N by P matrix P. That's just too many words. You multiply your row by columns, okay? So that's what we're going to do. Take your row, multiply it by your columns, add those products up. Go same row, next column, add the products. That's all we're going to do over and over throughout the whole process. So for example, find AB. The first thing we're going to do is we are going to write out the dimensions of AB, okay? So the dimensions of A, it's 2 rows by 2 columns. The dimensions of B, that is 2 rows by 3 columns, all right? First thing I check, inner right here. Are they the same? Yes, they're the same. I can multiply, all right? The next thing I check are the outer. That's what my answer is going to be. So AB will be a 2 by 3 matrix, okay? And now I'm just going to do row by column. Again, this should be, keyword review, all right? So I'm going to take these and I'm going to multiply. All right. I'm going to start out with the first row of my first matrix and I'm going to multiply it by the first column of my second matrix, row by column. So I'm going to say 2 times 4 plus -3 times -3. We're just going down that row. That is my first term or first element in this guy. Then I'm going to go to the next one. Same row, second column, right? Do exactly what I just did. I'm going to say 2 times 6 plus -3 times 1. Then I'm going to do the next one. Same row, third column. And I'm going to say 2 times 2 plus -3 times -5. Once I run out of columns, I'm done with that row. All right, and I'm going to go on to the next row. So I'm going to start the whole process over, but I'm going to do it then with my next row. All right, so next row, first column. And I'm going to do that whole thing all over again. I'm going to say 1 times 4 plus 5 times -3. Same thing with the next column. I'm going to say 1 times 6 plus 5 times 1. And then go on to my third column. Going to say 1 times 2 plus 5 times -5. Quick check here, all right? Quick check. The first thing I check to make sure that because here's the thing, not hard, lots of room for error, okay? Because you're just writing these numbers down. So the first thing I do is I check my rows. So this should always be 2, -3, 2, -3, 2, -3. Those should match. 1, 5, 1, 5, 1, 5. Those should match, okay? Then I check columns, 4 and 4, -3 and -3, 6 and 6, 1 and 1, 2 and 2, -5, -5. So that I always do that quick check because at any point you can forget a negative or something, right? And then you just messed up your whole answer. And then all you do is actually order of operations here. So now we're going to find the elements by doing the process. This guy is going to be 8 plus 9, right? -3 times 3. So this guy is going to be 17. We have 12 plus -3. That's going to be 9. We have 4 plus 15. That's 19. That's my first row. Down here we have 4 plus -15. That's -11. We have 6 plus 5. That's +11. We have 2 plus -25. That's -23. That is my answer. If I were to flip these, so let's say I would say, can I do B times A? Well, B is a 2 by 3, A is a 2 by 2. In this case, if they wanted me to flip it, I would say, no, I can't do that at all. So there are going to be times when if you were to do it in a different order, you can't do it at all. And there are going to be other times when you do it in a different order and it actually will change even the size of your answer. Okay? So when I look at this, I can see it's going to multiply both ways. But one way I do it, I'll get a 3 by 3. The other way I do it, I'll get a 2 by 2. I'm still going to do row by column. It will feel differently. So I'm going to say row by column, column, column when I do it this way. When I do it the other way, it'll be row by column, column, because I'm actually doing it in a different order. All right? All right, given matrices A, B, and C, and scalar K, these properties apply if the products are defined. So that's key. If the products are defined, means make sure you can do them. So associative property, it does work. So you can multiply them, these two first and then that one, or these two first and then that one, but you cannot switch the order. Okay, so you cannot switch the order, but you can group them. Associative property is scalar. Scalar works even if you're multiplying matrices. So you can multiply the scalar after you do the multiplication. You can multiply it to one of them and then do the multiplication. It doesn't matter. But you cannot change. You notice the A-B order did not change here. Same thing. Distribution works either way. It works. But you'll notice, I want to point out, when A was in front here and it distributed, it was A, B, A, C. When A was in back and it distributed, notice the order. It was B, A, C, A. All right, so it is maintaining the order that it gave it to you, even when you apply these properties. The only thing that doesn't change is when you're multiplying by the identity. It doesn't matter which way you multiply, you're always going to end up with what you started with, because it's always going to be a square matrix, right, when you do this, and so it's going to give you the same answer. All right. You can use matrices to set information up that's easy to see, and then you can quickly do some matrix multiplication to calculate more information. High school basketball coach records individual statistics on a spreadsheet. The illustrated portion shows the shots made by his top 3 players during the first 10 games of the season. Write matrix S representing each player's made shots, and matrix P representing the point value for each type of shot. Then write and evaluate a matrix expression representing the total points for each player. So basically what we're going to do is we're going to take this first part right here and do a matrix, okay? With these 3 players. So if I were to write a matrix for the players and the number of shots they made, and they gave me what to do. It doesn't matter what you label it, but they told me. I'm going to label it exactly how they have it. 2 pointers, where that was 80, 59, and 55. 2 pointers were made. 3 pointers, that was 21, 15, and 5 for them. And then free throws, that was 19, 12, and 9. Okay. It actually wants me to use this to figure out how many points each player scored. So when I set up my point one, I'm actually going to do it down. So how these went across and down, I'm going to do a column that represents how much each shot would be worth, right? 2-pointer, 3-pointer, free throw. That's what those are worth, right? Obviously. And I'm going to do it just like that, okay? Because if I want to figure out how much this first guy made, I would multiply 80 times the 2 to give how many points he got in 2 pointers. I would multiply 21 by the 3. That's how many points he made in 3 pointers. And I would multiply 19 by 1. That's how many points he made in free throws. And I would add all of those up. Well, that sounds a lot like matrix multiplication, right? And so that's what they're asking me to do. They're asking me to logically set this up where then when I multiply those, it gives me the value for each player. All right. And so that's what we're doing. So if we were to multiply those, we would take Freeman's, and this is actually going to be a column matrix when I'm done, right? So this is a 3 by 3 and this is a 3 by 1. So we have a 3 by 3 and a 3 by 1. I should have a 3 by 1. I should have a column matrix when this is all done. And so I'm going to do exactly what I would do here. I would say 80 times 2, right? So I have 160. Plus 21 times 3, that's going to give me 63. 19 times 1, that's Freeman. Gonzalez, that's going to be 80 times 3, or 59 times 3, rather, sorry. Then I have 59 times 2, 15 times 3, we'll get it out eventually, 45, and 12 times 1. And then 55 times 2, 5 times 3, and 9 times 1. And I can figure out how much each player actually scored in the games. Obviously not one gamer. That is one monster of a basketball game.